All right. Well, welcome to Online Finite Mathematics. I know this wasn't the plan for the semester, but we will make the best of it. So, my plan for these lectures is I'm going to go over the same things that I would have gone over in class. It might go a little bit faster just because you guys can pause the lecture at any point and rewind and things like that. And then I also don't need to allow for questions because I'm recording these. But you are welcome to email me any questions you have if you have any questions about these lectures. Um, I also strongly recommend taking notes during these because they're just like a regular lecture. Just pretend like you're in class watching through these lectures. So, anyway, for this one, we're going to start off with some clicker questions, and then we will jump into the lecture. So what I want you to do is pause the video right now and work the question on the screen. So an account contains $1,000. It earns 0.75% interest compounded monthly. If payments of $500 are made monthly into the account, how much will it contain in 2 years? So pause the video, actually do this. This is important. Pause the video and calculate it. All right. So what you should have ended up with is answer C, $13,101.75. If you ended up with option A, then you put the $1,000 in as positive. So the fact that the account contains $1,000 is not any different than depositing $1,000. It's negative either way. So the reason why I bring this up is for the project, which you are hopefully working on this week. In that project, there are a number of different investments where you have a present value and a payment. It's really important to have your negatives correct. So, all right, let's move on to the next question. So same question, but we want to know how much interest was earned over the 2 years. So again, pause the video and calculate this one. All right, so what you should have ended up with is answer C, $101.75. And that's because the contributions were $13,000, so that's $500 times 24, so that's $12,000, plus the initial $1,000, so that's $13,000 that was deposited. And if there's $13,101.75 in the account, the difference between those two things is $101.75. So remember, interest is just the difference between how much you put in and how much you take out. All right, let's look at the next one. This one just asks for the contributions, which we just talked about. It's answer C, $13,000, $500 a month for 24 months, plus the initial $1,000. The ending balance after 2 years is going to be the final amount in the account. It's going to be the future value that we just solved for. The reason for these questions is because they're very similar to things you're going to have to be doing in the project. So the final or the ending balance, which is something you have to find in the project a lot, is not just your contributions. When you deposit money in the bank, the ending balance is all of your contributions plus any interest that you earned. So the answer here is C, $13,101.75, which is the 24 payments of $500, the initial investment of $1,000, and the interest, $101.75. All right, so now just a couple questions that I usually ask in class to make sure you're following the instructions for the group project. So did you follow the instructions in the big yellow box on the front page, and did you designate a group member to email the project in? Hopefully the answer there is yes. If you haven't, do those things. Next, how should the project be submitted? Correct answer here is D, by emailing one copy of the project to me and to all of the other group members. Now, this semester is a little bit different. If you don't have group members, then you're just submitting the project to me. But if you're working in a group, you need to be emailing the project both to me and to those other group members. All right, if it is not your job to turn in the project, it is your job to check to make sure D, all of the above. You have received the project by 5 p.m. on the due date. That's this coming Friday. The project was sent to all members and myself. And the project is attached and is the correct version of the project and opens correctly. So if someone else in the group is turning in the project, you should check to make sure you got the project. You should download it, you should open it up, and you should look through every tab to make sure that it is the correct version. I've had groups submit completely empty projects, so they accidentally submitted the file that they downloaded. I've had groups submit partial projects and all sorts of things. So this is a good life lesson for when you get a job or anything important in the future, whether it's a class project or a work project or whatever. If someone is in charge of turning something in, you should double check to make sure that it was turned in correctly. So, all right. So that's kind of our intro for this lecture. All right. So what we're going to talk about in this video is we're going to talk about accounts that decrease in account balance over time. So savings accounts, for example, increase over time, right? You're depositing money over time, and so the account balance goes up. But there are accounts where the balance goes down as well. So a couple examples of those are loans. So when you take out a loan, you pay back the loan over time, and the account balance goes down. Retirement accounts, which is the example that we're about to do, that's another example of a balance going down. So you save up until retirement, and then once you hit retirement, you start spending the money you've saved up, and the account balance goes down. And then the lottery, winning the lottery, which we know you won't do because we know probability, that's another example, and we'll go over one of those as well. So, all right. So, let's look at our example. Suppose you plan to save for retirement by making monthly payments for the next 30 years. If your account earns 2.5% compounded monthly, and you wish to withdraw $5,000 per month for 25 years for retirement, how much should you deposit per month for the next 30 years? All right, so this is a two-part problem, and you'll see some two-part problems in the homework as well. So first, we're saving up money, and then we're going to be withdrawing that money over time to live on. So we can kind of think of it as we're starting at $0. We're saving up money until retirement by adding in payments. And when we invest those payments into the bank, we're going to invest them so they would be negative. So that's per month into the account. That's going to be over 30 years. 30 years. And that's going to give us some value, X dollars. We don't know how much that is, but we need to figure it out. Then, over the next time period, we want to take out $5,000 per month. So that's going to be a positive $5,000 a month because that is an amount of money coming to you. I know those kind of seem reversed as far as positive and negative, but remember that in the TVM Solver, money moving away from you into the bank is negative. Money coming back to you is positive. So that's positive $5,000 back to you that you can spend on retirement. That's going to be over 25 years. And then we're going to end up with zero, because the idea is we want to find out what amount of money we need to be able to withdraw $5,000 a month for 25 years to make the money last exactly 25 years. All right, so there's two things we don't know here. We don't know X, the amount of money we need to have saved up to withdraw that $5,000 per month. And we also don't know the payment. So that's how much money should be deposited now to save up for 25 years. So if we kind of look at these two scenarios, we've got starting at X and ending at $0. There's one unknown. X is the only unknown there. If we look at the first part of the problem, going from $0 to X dollars, there's two unknowns. We don't know the payment and we don't know X. So in these two-part problems, you need to figure out which part you can solve for first. And for us, that's going to be this part, the second part. We can use the fact that we want to withdraw $5,000 a month and end with $0 to find X, how much we need to retire on. All right, so to do that, we'll get our calculator out and our TVM solver. All right, so we're wanting to make withdrawals for 25 years. So that's going to be 25 years times 12 per year. So that's going to be 300 withdrawals. The interest rate, let's see, we said that was 2.5%. So we put in 2.5. The present value, that's what we're trying to figure out. How much do we need to have in the account to be able to withdraw that $5,000 per month? All right, so the payment, that's going to be a positive $5,000 a month because that's money coming out of the account. Future value is 0 because we want to end with $0. And then payments per year and compounds per year are 12. It doesn't mention anything about payments being made at the beginning of the time period, so we'll leave that at end. So what we're trying to solve for is our present value. And so we get that that is $1,114,537 and about 11 cents. So let's write that down. $1,114,537 and 11 cents. So that's X. That's the amount of money we need to retire on. Now we can use that amount to solve for our payment. How much do we need to invest over the next 30 years? All right, so in our calculator, we'll go ahead, let's zero out the first 5 things here. All right, so we're saving up for 30 years. So 12 payments per year times 30 years. It's going to be 360 payments. Same interest rate, 2.5%. Present value is 0. We're assuming we're starting at 0. Payments, what we're looking for. And the future value, that's what we're trying to save up to. That's the $1,114,537.11. So now what we want to do is find that payment. And so just solve for the payment. And what we get is that payment would be $2,081 and about 82 cents. And so that's how much money you would need to deposit now to be able to save up the $1,114,537.11 to be able to withdraw $5,000 a month for 25 years. If we wanted to find the interest for this, what we could do is take our payment, $2,081.82, multiply that times the number of payments, 360 payments, and we would get that that's $749,455.20. So that would be the amount of money you would put into this account. The amount of money taken out of the account is the $5,000 times 300 payments, the 25 years of monthly withdrawals. And that is $1,500,000. And the difference between those two numbers, if we subtract them, is $750,500. $544.80. So you actually end up earning more money in interest here than you actually put in the first place. And so that's kind of the beauty of compound interest, and also why you should start saving money for retirement early. Because the earlier you start saving for retirement, the more time compound interest has to accumulate more money. So, all right, let's move on to our next example. At graduation, Clark owes $25,000 in student loans. His loan requires monthly payments for 10 years at 5.5% interest. After making 80 payments, his grandfather gives him $10,000 to pay off the loan. Is it enough to pay off the loan? All right, so there's a couple questions in the homework you'll see like this. It's basically, how much does he need to pay off this loan? And it's actually two pretty easy steps, one of which you already know. So step one is going to be to find his payment. And so let's go ahead and do that part. So this is going to be very similar to other loan questions we've done. We'll go ahead and zero out the first 5 fields on our TVM Solver. All right, so he's making monthly payments for 10 years. So that's monthly 12 times 10 years. So that's 120 payments. Interest rate was 5.5%. The present value, that's the amount of money he owes. That's $25,000. It's going to be a positive number because when you get a loan, that's money given to you. So that's positive. Payment's what we're looking for. Just like every other loan, our future value will be 0 because Clark wants to pay off this loan over those 120 payments. And then the payments per year and compounds per year are 12. All right, so let's solve for our payment. And we get $271 and about 32 cents. All right. Now, the way the TVM solver works is the present value is how much money you owe within payments remaining. Okay? So, if I change that to 119 and solve for the present value, $24,843.27, that would tell me how much you would owe after making the first payment. So that's 119 payments left. Or if I changed it to 118 and then solve for the present value, $24,685.82, that tells me how much Clark would owe after 2 payments. So in this case, Clark has made 80 payments out of the 120 payments. So that means he has 40 payments left. So first, let's go ahead and write down our payment, $271.32. And then write down our second step, which is to find the present value within payments remaining. And in this case, since Clark has made 80 of his 120 payments, that means he has 40 payments left. So we just set in as 40. That's how many payments he has left. And we solve for the present value. And what we get is that it would require $9,895.27 to pay off his loan. So the very generous gift from his grandfather of $10,000 would pay off his loan with about $100 to spare. So what we can't do here is just take the payment and multiply it times how many payments he's made. Because the thing about that payment, that $271.32, is not all of that payment actually goes to paying off his loan. Only part of that does. The other part, the interest part, is taken by the bank. So if we just multiply that payment times 80, that's finding us how much he's paid, but that doesn't mean how much he has paid off of the loan, just how much money he has given to the bank. And the bank has taken part of that money for profit. So Now that we've kind of discussed that, let's look at an amortization schedule because that's going to be pretty helpful in kind of figuring out how these loans work. All right, so here is our amortization table. It's actually the exact same example that we were just looking at. So $25,000 loan at 5.5% interest with 10 years of monthly payments. And so we already looked at how to find the payment itself. We found that in the TVM Solver. So now we just want to look at how to find the other pieces. So what this table tells us, so there's a payment number next to each payment. And so if we were to scroll all the way down on our table, all the way down to the bottom, we would get to the 120th payment, the last payment, and that's where the loan gets paid off. It actually shows, because our payment is slightly rounded up, that we would have actually overpaid by about 69 cents. We won't worry about that in this class. The bank would take care of that. The very last payment would be 69 cents cheaper to account for that. But anyway, so we have every month's payment for all 120 months. All right, so every month of the loan, that $271.32, that the payment of that amount is made. What happens when that payment is made is the interest amount is taken out. So the very first month, $271.32 is paid. $114.58, that's taken by the bank or financial institution. That's their profit. That's the cost of borrowing money. And so what's left over is the amount that's applied to your loan. So every month you make a payment, the bank takes part of it, the remainder is used to pay off your loan. All right, so let's find that interest amount. So the interest amount is actually just simple interest. So in this case, it would be I equals, P is our present value, which is currently $25,000, times our rate, which is 5.5%, so 0.055, and then times the time. So the entire loan is 12 years, but that's not what we're looking at. We're not looking at the entire loan. We're looking at one payment of the loan. And one payment represents 1/12 of the year, because 1/12 of the interest rate is charged every month. So we multiply that by 1/12, and that's T. So I equals 25,000 times 0.055 times 1/12, and that gives us $114.58. So that's where that number comes from. It's just simple interest on the balance from the previous month. So then what we do is we take the payment amount, $271.32, and we subtract out the interest amount, because that's what the bank takes out. That's their profit. That's the cost of borrowing money from the bank. And that equals the amount applied to principal, $156.74. So just the difference between how much was paid and how much the bank took out. Now, the loan balance, it doesn't go down by the full payment amount because the bank took part of that payment. The balance goes down by the applied to principal. So it goes down by $156.74. So we take our $25,000, subtract out our $156.74. That gives us $24,843.26. The second month, the payment stays the same, still $271.32, but the interest amount changes. And that's because this time the calculation is I equals, P is no longer $25,000 because after making the first payment, you don't owe $25,000 anymore. Instead, you owe $24,843.26. And we multiply that times the interest rate, 0.055, times the time, which again is 1/12. So it doesn't matter that it's the second month. That doesn't make it 2/12. 2/12 would be 2 months out of the year. Every month, we're just calculating 1 month's interest at a time. So we're multiplying by 1/12 because, again, each month 1/12 of the interest rate is charged, and that's because payments are being made monthly. So if payments were being made weekly, for example, we'd multiply by 1/52nd because each week 1/52nd of the interest rate would be charged. So when we multiply those together, we get our interest amount, $113.86. Take our payment amount, subtract that out. That gives us our amount applied to principal, which is a little higher than the month before because the interest amount is a little lower. So $157.46, that is applied to the balance. So we subtract that out of the balance, so minus $157.46. And that gives us our new balance, $24,685.81. And then we just repeat the process every single month. So we take the balance multiplied times the interest rate times 1/12, and take that, subtract it from the payment to get the applied to principal, and then subtract the applied to principal from the balance, and just repeat the process. So notice here that the interest amount is not based on the payment. The P is not the payment. The P is the balance owed at the end of the previous month. So that's how our amortization schedule works. All right, let's look at one more example. All right, the final question that we're going to look at today, the winner of a $1.6 billion lottery jackpot can choose between 29 equal annual payments or a lump sum payout of $950 million. What interest rate does this assume? So this is actually how the lottery works, and this was the largest lottery jackpot in history. It was a few years ago, but anyway, basically, the idea of the lottery is whoever organizes or runs the lottery, the person who won $1.6 billion, the lottery organizers don't have that much money. That's how much money they can pay out over 29 years, assuming some certain rate based on the amount of money they have. And the amount of money they have is $950 million. So either you can just take the amount of money they have, the $950 million, or you can let them keep it and invest it, and they will pay you that amount plus interest over 29 years, which ends up giving you all $1.6 billion. So theoretically, you could take the $950 million, you could invest it yourself, and you could end up with $1.6 billion in total over 29 years, though most people that do that end up spending it all and going broke. So anyway, all right, so let's look at how to work this one. So we'll just go through what we would type into the TVM solver. So N, that's going to be the number of payments. In this case, that is 29. There's 29 equal annual payments. Our interest rate, I%, that's what we're looking for, so we don't know what that is. The present value is how much that series of payments, the sum of that series of payments, is worth right now. And so what that series of payments is worth right now is $950 million. So that is the present value of $1.6 billion split up over 29 payments. So we're saying that those two amounts are essentially the same. Remember, this unit is about the time value of money. So the idea here is that $950 million today is worth $1.6 billion spread out over 29 years, assuming some interest rate. So that lump sum payout is the present value. When you get to this question in the homework, that's going to be the amount you're solving for. So I changed up the example just a little bit, but everything else about the example will work the same, other than you're solving for the present value instead of the interest rate. All right, the payment. So the payment is the amount of money you would receive every year. And so the payment is the 1.6 billion, so that's $1,600,000,000. So It's a whole lot of zeros. So that is $1.6 billion divided by 29. So those are the payments. The amount of money you would get each year, splitting that 1.6 billion up over 29 payments. All right, and then the future value. The future value is not 1.6 billion. That's a common mistake on this problem because you would have 1.6 billion, assuming you could receive those payments every year for 29 years and not spend them. But that's not the idea here. The idea here is from the perspective of paying out the lottery. And so that is going to be 0. Also, I forgot to mention this. Our present value should be negative because essentially you would have to invest $950 million. The people organizing the lottery would have to invest the $950 million to pay out those payments. So present value is negative. All right, so then number of compounds per year, that's going to be 1, and the number of payments per year, also 1, and that's because we're looking at annual payments. All right, so let's grab our TVM solver. Our N is 29. It's the number of years, which is also the same as the number of payments in this case, since it's 1 per year. Interest rate is what we're trying to figure out. Present value, that is going to be, got to get down to my negative button. There we go. A negative $950 million. Whoops. Yeah, that's right. Actually, we don't need a comma there. Let's delete that. All right, $950 million. The payment is $1,600,000,000. It's a whole lot of zeros. Divided by 29. So we're splitting up that payment over 29 years. And this is the exact same thing you'll do in the homework. Is we are taking that payment, we're figuring out the payment based on just taking the entire amount of the lottery jackpot and splitting it up into those 29 payments. And so what we end up with is $55,172,413.79. So that's how much money you would get paid each year for 29 years with a $1.6 billion jackpot. And lastly, our payments per year and compounds per year are both 1 since it is annual payments. All right, last thing to do is solve for the interest rate. And we get that it would be about 3.884% interest. So assuming that interest rate, you could invest $950 million today and pay out $55,172,413.79 each year for 29 years, which would sum up to $1.6 billion. All right, that's it for today. Good luck with your homework this week.